Knowing how to interpret and pull information out of graphs is an extremely powerful tool, especially in physics. And today we're going to be talking about 3 different graphs, and we're going to be showing all the different information that you can pull out of it. All these are going to be motion graphs. We got our displacement versus time graphs, our velocity versus time graphs, and our acceleration versus time graphs. There's lots and lots of really good, rich information that you can pull out of these graphs about the motion of an object. And with that said, let's dive in. All right, so before we get started, we're going to talk about how you can find the slope of a graph. So you remember in your math classes you had the equation y equals mx plus b, right? And you know that m was considered the slope. And your slope is equal to the rise of the line divided by the run of the line. All right, so down here we got a little graph. Let's just draw some sort of a line here. Something like that, okay? Now, let's see here. Let's not use that color. Let's use this color. So remember that the rise is what goes up the graph and the run is what goes horizontally. So if we were to take the rise and run from here to here, so your rise is your y2 minus y1 divided by x2 minus x1. And so that's your rise. How much does it go up in the y direction? Your run is how far it goes over in the x direction. And that gives you slope, okay? Now this is actually going to be super informational and really useful later on as we go. But I just want to put that in your brain before we continue any further. So the first type of graph we're going to look at is a displacement versus time graph. And we want to do a displacement versus time graph of a parked car. We're going to see what that looks like on a displacement versus time graph. Well, before we, start graphing this, what is a parked car doing? Well, it is not moving, right? There is no motion in a parked car. It just kind of stays in one spot. So does its displacement ever change? Well, the answer is no. So your displacement would be really just a flat line. And if we said that it started at 0 displacement, well, it's going to end at 0 displacement, right? But in reality, this line could be anywhere. It could be up here as well. Because if it started, and let's say this is 5, if it started at 5, the parked car is going to stay at 5. So as time is going by, there's no change in its displacement. So let's write that down. No change in displacement, okay? And that's about as basic of a displacement versus time graph as you can get. Wherever it started, that's where it's going to end. There's going to be no motion if in a position versus time graph of a parked car, that is. We're going to go and look at some other ones where there actually is some motion. All right. Let's look at this car right here that is on cruise control. So that means, before we jump into the graph, what does that actually mean that the car is doing? That means that the car is moving at a constant velocity. Okay, so moving at constant velocity. So its speed is not changing, it's not speeding up, it's not slowing down. You're driving down the road 55, 65 miles an hour, you hit cruise control, and you just stay at that speed. So what is that going to look like? Well, that means every second or every section of time, you're covering the same amount of distance, or you have the same, you're constantly increasing your displacement. So that means that you would have a graph that looks something like this. So every period of time, you gain the same amount of distance, or you move further and further away from your starting point. Okay? So on a a displacement versus time graph, if you're moving at a constant velocity, you're going to have a nice straight flat line like this. Or it's not really flat, it's got a slope to it, right? So there is going to be a slope to this. Now let's go and talk about that slope, because like we talked about earlier, slope is going to be important in all this. Well, what does the slope actually tell us? That slope actually has some information for us. Well, let's just kind of deconstruct this a little bit, and we're going to mathematically figure out what the slope means on a displacement versus time graph. So you remember that slope is equal to rise over run, right? Well, in this case, what is your rise? Your rise is your displacement. So you got your displacement, and your run is time. So displacement divided by time gives you the slope. And you remember from your kinematic equations that displacement divided by time actually gives you velocity. So with all that said, the slope of a graph on a displacement versus time graph is actually going to give you the velocity. That's an important piece of information. So whenever you're looking at these displacement versus time graphs and you see these different slopes, that's showing you how fast the object is moving. The steeper the slope, the faster it's moving, the more flat the slope is, the slower it's moving. Okay? So taking that, the idea of slope, and the steeper the line is, the faster it's moving and whatnot, let's go and do another displacement versus time graph, one where a car is speeding up. Now, if a car is speeding up, what do we call that? We call that acceleration, exactly. So acceleration, all right? So if the car is accelerating, what is that going to look like on a displacement versus time graph? Well, that means it's going faster and faster, right? So it's going faster and faster, which means the slope is getting steeper and steeper, right? Okay, so steeper and steeper. So what would that look like on a displacement versus time graph? Well, you start off with maybe a small slope, and the slope over time is gradually getting steeper and steeper and steeper. So it's going to end up being a curved line. So you're going to have a curved line whenever you're showing acceleration. So curved line shows acceleration on a displacement versus time graph. And you could figure out the velocity or the average velocity in different sections of this, but you notice the first little section right here, it's not that steep of a line, but then it gets steeper, and then it gets a little steeper. And if we were to continue this up, you would notice that the average of this curve is getting steeper and steeper, which shows that the car is going faster and faster and faster. So anytime you see a curved line on a displacement versus time graph, that means there's some sort of acceleration going on. But just for fun, let's look at a couple different curved lines here. If the line is curving but the other way like this, that shows that it started off really steep, right? That's a really steep section. And then it got less steep, and then it got even less steep as you went forward. So what does that mean? Well, that means that it's slowing down. Okay, so you started off with a really high velocity, and then you got to a lower and lower velocity. You know that because the slope is getting more and more flat. Let's look at another one actually. I didn't actually plan on going this in depth, but why not? Let's say you have what about a displacement versus time graph that looks like this? Okay, well let's just break it up section by section. Well, here you got a really steep line, but it's going downward. If it's going downward, that means you're just going backwards. And then let's see here. Then we got a less steep line, and then we got a even less steep. So it's getting flatter and flatter. So you would think that this would mean maybe you're slowing down, and that would be completely true. And you're slowing down because you notice that these lines are getting closer and closer to being flat. Now you're accelerating backwards, but you're getting closer to a zero velocity whenever you're doing that. Let's do one more of these. Let's look at one more situation. So let's get my color here. What about a curve like this? What do you think that means? Well, if you look at it section by section, that's not a steep line. And then it gets steeper, and then it gets steeper. So what does all that mean? Well, this means you're speeding up. You're just speeding up backwards. You're going faster in the negative direction. Okay? So that's everything on displacement versus time graphs that you need to know. What about a velocity versus time graph? Okay, so we're going to go over the same scenarios of a parked car, a car going on a cruise control, and a car speeding up, and we're going to see what those graphs end up looking like. So if we're talking about a parked car here, well, what does a parked car look like on a velocity versus time graph? Well, before we graph it, what does that mean? That means there's no motion, right? So no motion. That means that the velocity is equal to 0 meters per second. Well, where do we represent 0 meters per second on a velocity versus time graph? We represent it right here on the x-axis. So this right here shows 0 meters per second on a velocity versus time graph. So this is how you would represent no motion. It would just be a flat line on the x-axis for a velocity versus time graph. And there's no change in velocity. It's not speeding up, it's not slowing down, it's not moving. It's just staying still, and you just draw your flat line on the x-axis of your velocity versus time graph, and that's it. Nothing else to go for there. Now let's go down and look at a car that is on cruise control. All right, so this means you got a constant velocity, right? So constant velocity. So your velocity is not changing, and it's not 0. So your velocity does not equal 0 meters per second anymore. So you can't draw a flat line on the x-axis, so what do? Well, you got to have some sort of line above, or it could technically be below the x-axis too, but some sort of flat line that is not on the x-axis to show 0 meters per second. So here is how you would represent the velocity, or sorry, a constant velocity on a velocity versus time graph. Now, there's some very interesting information that you can pull out of this situation right here. So on a velocity versus time graph, you got this area underneath the line from here to the axis point. Well, what does that area represent? It actually gives us a little bit of information right there. So let's see here. If you look at this, this kind of looks like a square, right? Kind of makes a squarish shape. And how do you find the area of a square, or a rectangle, I should say? Well, it's the length times the width, right? So we'll call this length, call this width. So our length is velocity. Our width is time, so velocity times time. And what does velocity times time mean to us? What does that even mean? Well, if you remember your kinematic equations, again, the velocity equals displacement over time, we can rearrange that equation to say velocity times time equals displacement. So if you notice here, velocity times time is going to equal displacement. So the area is equal to the displacement. And that is true for a velocity versus time graph. The area underneath the line is going to tell you the displacement of the vehicle. How far did it move? Now let's go on and look at the car that is speeding up or accelerating. All right. So what is that going to look like on a velocity versus time graph? Well, I already said the car is accelerating. And that means that there is a change in velocity. That means the velocity is not staying constant anymore. So you can't draw a flat line. So what would that look like? Well, if the car is speeding up, that means the velocity is increasing over time. So you would start off with a low velocity, and the velocity would keep going up right here. Okay? So this right here would show a car accelerating. You started off with a low velocity down here, and then you ended with a higher velocity here as time went by. So therefore, you accelerated, you sped up. And that's what the graph would look like. Pretty simple, right? Now, we have a slope. And in this case, well, we know the slope has to mean something, because we did this big talk about slope earlier. We talked about on a displacement versus time graph, the slope tells you the velocity. Well, what does the slope tell you on a velocity versus time graph? Well, let's try to mathematically figure it out here. So slope is equal to rise over run, right? Well, the rise on this is the changing velocity. So your velocity is changing as it goes up. And the run represents time. Well, you remember from your kinematic equations that the change in velocity over time is equal to acceleration. So you got acceleration. So on this one, the slope is equal to acceleration on a velocity versus time graph. You might say, well, what about underneath the graph again, right? This area underneath here. What does that mean? Well, it still is your displacement. It's just that in this case, you have this triangle shape. And instead of finding the area of a square, you would find the area of a triangle. Oops, let me erase that. You would find the area of a triangle, and the area of a triangle is 1/2 base times height. Okay, and then your base would be the time, your height would be the velocity. All right. Now that's everything on velocity versus time graphs. So let's go down here and talk about acceleration versus time graphs. And you noticed I have the parked car and the car on cruise control sitting here next to each other. And the reason why I have both of those sitting next to each other is one thing. Both of these, there's one fact that is true. The change in velocity on both of these is 0. There's no change in the velocity. And I could also say that the acceleration is equal to 0 meters per second squared. So in both of these cases, there is no acceleration. So your acceleration versus time graph would just be a flat line right here on the x-axis. And because of this, it kind of makes the acceleration versus time graphs a little weaker. It doesn't give you as much information as maybe you would like to know. And we actually don't use these graphs that much, but that's what it would look like. There's no change, there's no acceleration at all going on these graphs. So therefore, it's 0 acceleration. And so if you get a graph that looks like this with a line going across the x-axis, you can't tell if the object is moving or if it's not. You can only tell if it's accelerating. And so that's, makes it a little hard to pull information out of an acceleration versus time graph. But that's what they both mean. So there is no acceleration on both of those. And that's what it would look like. But what if you had the car that was speeding up? Well, this, like always, like we've been saying for a while, that is acceleration. What does that mean? So we're going to assume that it's accelerating at a constant rate. Accelerating at a constant rate. So it's got a certain acceleration and it keeps accelerating at that rate. Well, what would that look like? Well, it would honestly just look like this right here. So this is what constant acceleration looks like on an acceleration versus time graph. It's just a flat line. Now, there is some information that you can pull out of this. Okay, so if we take this area underneath here, and we know that's a square, or a rectangle, I should say, and the area is going to be equal to length times width. Our length is time, our width is acceleration. We'll say that way. It doesn't matter which way it is. So we'll say time times acceleration. Well, what does that mean? What does that even equal? Well, if we remember, our acceleration equals change in velocity over time, we can rearrange that to say change in velocity is equal to acceleration times time. So you notice these two equations are basically the same, which means that is the change in velocity. So the area on an acceleration versus time graph tells you the change in the velocity. It doesn't tell you the velocity, it tells you the change in the velocity. It doesn't tell you how fast you're going in the end. It just tells you, how much your velocity adjusted as time went by. So once again, it's kind of a little bit of a weak graph. It doesn't give you a ton of information. It doesn't tell you if you're going 500 meters per second at the end or if you're going 20 meters per second at the end. All it tells you is how much your velocity changed. And there you go. Now, some of you are probably out there saying, Okay, yeah. So what if there is an acceleration versus time graph that looks like this, right? So you got the area underneath the line, and that would still tell you the change in the velocity, like it did up here. But some of you probably are asking the question, well, what does the slope on this mean? So a slope on this one is going to be the change in acceleration. So what do we call the change in acceleration? Well, to be honest with you, we never ever use this in physics, but because you asked, the change in acceleration is called a jerk. Sort of like if you feel a jerk or a jolt or something like that. That's what we call it. And then there's going to be someone else out there that asks, well, what's a change in jerk? Well, a change in jerk is actually called a snap. And then there's going to be someone else out there that's going to say, well, what do we call a change in snap? Well, a change in snap is called a crackle. And then there's going to be someone else out there that says, all right, hold on. Let me get all of this straight. So a change in displacement, we call that velocity. A change in velocity, we call that acceleration. A change in acceleration, we call that a jerk. A change in jerk, we call that a snap. A change in snap, we call that a crackle. What do we call a change in crackle? Well, believe it or not, and this is 100% true, the physics community has come together and we've decided that a change in crackle will be called a pop. Well, anyway, thanks for watching. I hope you learned something. If you did learn something, hit the like button. And if you want to watch more videos, make sure to hit the subscribe button. Really appreciate it. If you have any questions, comments, want to add anything, put it in the comments below. I got a couple of links in the comments to other videos that might also be helpful to you in the future. So go and watch those if you need more help. And have a great day. Thanks for watching.